All right, let's do Embodied Cognition 2. So this is going to focus entirely on a different approach, that of robotics. And hopefully it'll be interesting. So typically, when we think about intelligence or we think about cognition, we think about defining items or understanding what our goals are, our tasks, and executing them somehow. That's typically what we do with computers. So in a classical cognitive architecture of computationalism, you might define what a chair is. You might build it into the system. If you think that it's biological, like Jerry Fodor, it might be like an innate concept, which is strange, but sure. If you're a connectionist, you might base what a chair is on chair use behavior. So mapping on when you can successfully sit down versus not, you'd eventually like fail enough times to get it right and come up with a rough set of processes that will give you the right answer every time, or most every time. That's typically going to be a supervised learning approach, which means that in both of the classical architectures, the solution to whatever problem you're facing is given to you in some way. But that seems strange. How could it be that our top ideas for how the mind is organized require some organizer? There's got to be something else going on. And so enter the field of biorobotics, which is an attempt to try to build up, go from the bottom up rather than top down. So the cognitive approaches we've been talking about always start with thinking about how the mind works and then figuring out how it's applied. Here you would think about starting in an embodied approach and then seeing how far that got you. So this is going to have some connections to perception, which again seemed like it was cognitive without being, or sorry, it seemed like there was processing that wasn't necessarily immediately cognitively accessible. So the field of biorobotics tends to use living organisms, and usually insects are a prime one, in order to attempt to understand how they work. And using that to develop our understanding of how our own minds and bodies work. So we've known since the days of Galvani and Volta that humans use electricity, or sorry, that creatures use electricity to make their muscles move, right? And we were able to do that to dead frogs. We could make them, their muscles twitch just by shocking them. So there's a thing that, like, there are processes going on in our bodies that seem like they are, that for them to work, you don't necessarily need an intelligent processor. It could be the case that the intelligent processor decides when to send out signals to let the muscles work, but that we'll start off with the assumption that the muscles work regardless of what is going on in the mind. In a sense, you can get bodily action without computing it. The body can move just by shocks being fired through you. And you knew that, right? Like, there's nothing surprising about that. Reflex behaviors are like this. So how complex can we make these reflex behaviors? How complex can we make any bodily action using very minimal assumptions about cognition? In fact, just the body. So in the field of behavior-based robotics, there's a couple of unique features that are helpful in understanding how they work. That might be helpful in illuminating and understanding how our minds work uh, with our bodies. First, it's not a centrally planned system, right? That's the thing I've been emphasizing. There's no entity that is going top down to decide how each particular part of the muscle will move. And secondly, it's real time. So all of that offline discussion that we had in the previous video, we're just going to ignore that for now. And then at the end, we're going to see if there's anything that we've learned from here to that could be useful in understanding how we plan our semesters and plan deeply into the future. So in a lot of the biorobotics approaches, we use something that's called the subsumption architecture. Basically, it's just a lot of subsystems. And these subsystems, we can call them layers if you want, are going to operate all the time and independently of each other. Imagine just linking a bunch of reflexes together and seeing what happens. If they interact in particularly complex, dynamic ways, it might seem like a cohesive sort of function emerges from very deterministic layers, right? If you have a reflex reaction that's connected to another reflex reaction that's connected to another reflex reaction, then some stimuli could create a fairly complex response. And so people have been trying to do this for decades. There was a fish called Wanda, well, a robot called Wanda that was able to move up its tail up and down at a certain speed and frequency. And it seemed like when you observed it, it was able to mimic a lot of fish-type behavior, suggesting that a lot of the things that seem like they're very complex really just depended on speed and frequency. Again, those could still be programmed from the top down, but we're seeing how far we can get here. We've attempted to design more complex objects. So in this case, this is a hand that it turns out can hold objects and can adjust based on the resistance it gets from the objects that you put in front of it. So it compresses around the object. Okay. Each of these is triggered by an object touching it, and it will apply some sort of pressure or some amount of pressure until it grasps the object. Cool. Doesn't seem to need to be that complex at all. Enter Alan. To imagine, just think of a Roomba, right? Like a Roomba can go around a room that it's never seen before using very simple algorithmic processes. Alan was a pre-Roomba, if you will. It could go around the room and avoid most objects that it encountered. We did this with a couple of other objects as well, Toto and Nerd Herd, that allowed, with just a couple of layers, you could react to an environment in complex ways that were presumably unpredictable, or at least would have taken a lot of programming to try to do separately. And each of these robots, I guess there's a sense in which you can say that it is representing the environment, but there's not it's not the same kind of representation that we have, right? It's a lot of it's just going to be purely reactive, almost physical. Let's see if I can play this in the PowerPoint, or if it's going to take me to a different slide or to a different video. This is where we are now. We have robots that can do all sorts of complex behaviors, things that even I can't do. I can do that one. Probably hurt myself trying that one and that one. My shoulders don't go that high. So this is going to involve lots and lots of layers, but the basic idea is simple. We've got an object that can go and behave in seemingly complex ways. Let's see, how do I get out of here? This is why I don't play videos during these recordings. All right. So the basic idea so far is this. There's lots of different ways of incorporating how the body fits into the mind. And some people have taken this to pretty far extents, right? That all of our mind is about bodily perception in some way. Some people don't want to go that far, but even the people that don't want to go that far, that don't want to think that everything, including advanced planning, is bodily, will nevertheless say that there are some behaviors that we thought might have been extremely difficult to program that it turns out are actually pretty easy to reproduce using very simple layers of responses. Subsumption architectures, somewhat akin to your reflexes, albeit a little bit more complex, but they don't even have to be that much more complex. All right, so one quick final slide on what problems we might have. We've gotten a good portion of the way here. And one thing that I think is interesting in considering embodied cognition is that the things that we thought might require lots of cognitive load might actually be much easier if you bring the body into bear again. In the discussion of the history of our thinking about mind, this goes back to Amo's discussion about how the mind and body were being unnecessarily separated by the modern philosophers. But there's no decision-making procedures going on in these biorobotic architectures, and by analogy, you would imagine the same thing for our own bodies. And so what do you do if the processes conflict? We've seen that discussion in modularity come up, and I mean, I think there's any number of answers that may be actual. But the point is that even if you want to be extremely skeptical of embodied cognition, there is less that you need for your mind to be doing if your body can lift part of the labor, can do part of the labor, or if the environment is going to come into play in your mind in some way. But that's still going to leave a lot of the extremely offline, far in the future, abstract processing and planning that we do to be very mysterious. This is the stuff that makes human cognition so special, and it seems like embodied cognition might get us a part of the way there, but you have to make quite a few assumptions to think that it'll get us all of the way there as an architecture of the mind. All right, so in the next video, we'll connect this to the next section, and it'll be fascinating. Trust me.